everybody to EE240. So this is the last couple lectures of this semester. So just a couple of administrative things. As I mentioned in the tape ahead, for those of you guys who are actually taking the class, make sure you're here on Thursday, because that's when we're going to do the HCAN evaluations. We definitely want to get your feedback and your inputs on the class. So make sure you're here. Other than that, the project is going on as we speak, which again I assume is the cause of the attendance at the moment. As you guys hopefully all know, the project presentations are going to be next Monday. They'll be at 9:30 a.m. over in the Berkeley Wireless Research Center. You can find directions on the web and all that, but hopefully most of you guys actually know where that is. The plan there is, you should, I forget exactly how many slides I said, but something like maybe 3 slides and like 5 minutes of presentation. In the past, people tend to sort of slide quite beyond that. So try and be fairly disciplined. We want to make sure we all sort of get out within a reasonable time frame. And the point of the presentation is really to kind of give a highlight as to what were the key points in both the design itself and perhaps more importantly in the methodology you used to come up with your project design. Now you'll notice that there is sort of a roughly 6-hour time window between when you'll be doing the presentation and when the project report is actually due. That's somewhat intentional because it'll still give you a little bit of a chance to, think about questions and et cetera that were asked, update the report and et cetera. But, obviously the point is you should be very much done by the time you get to the project presentation because if not, you really will not have very much time to continue working after that. So with that, any questions on either the project or material or anything? Oh, maybe one other thing I will mention, the final exam will be basically a week from tomorrow. If I remember correctly, it's 11 to 12, or excuse me, 11 to 2, something in that ballpark. And I'll sort of send out an announcement as to the exact room as well. As usual, I will do a review session, meaning that I'll just show up and answer questions. We'll probably do that on Tuesday, just sort of given timing of when the exam is and when the project is due. So if people have sort of specific preferences on timing for that, certainly let me know, but we'll probably figure the exact sort of logistics on Thursday. So any questions? Okay, so if not, let's actually go ahead and sort of wrap up with the material. So last time we basically finished talking about offset cancellation, or more generally, let's say, changing offsets inside of your circuits, or more specifically in the comparators as you care about in this project. So the last kind of couple of topics that I'd like to cover is first the sort of MOS sample and hold, meaning we've drawn a bunch of these switches in the past in our switch capacitor circuits, but turns out you actually have to build those things out of real transistors, and as we'll see, they have lots of issues associated with them. And then what we'll do briefly on Thursday is although we talked a little bit about using equalization as a method of sort of getting around some of the limitations of the channel response, we never really showed you any details as how you'd build those circuits. So I'll show you a few of the sort of simpler equalizer topologies, give you a few of the sort of key ideas there. We won't really spend a ton of time on it, but that's really what we'll mostly focus on Thursday. So with that, let's go ahead and dive in to talk some more about the sample and hold, or really the switches that we've been using inside of our switch capacitor circuits. So as we talked about several times previously, when we think about these sort of switch capacitor circuits, or really even just these simple samplers, our kind of conceptual model was something like this, right? We said that basically we would have some switch that would connect a capacitor to Vin. And of course, as soon as we turn that switch on, just instantly we would drive the voltage on the capacitor to track with the input. And then as soon as we turn this switch off, we would grab the exact value of Vin and sample it onto that capacitor. Now, unfortunately, there's no way you can actually implement something like this, right? We can only roughly approximate it. So as we talked about many, many times, of course, any real switch is going to have some resistance associated with it. And therefore, there will always be some KT over C noise sampled at the output here when you turn the switch off. So that, again, I think we know very well by now. Unfortunately, there's also going to be several other things that are going to limit the performance of these types of circuits. First, of course, is that because there's a finite resistance in that switch, there's only going to be a finite bandwidth in sampling. And we'll see sort of a couple of different ways that manifests itself. There's the sort of obvious way, which is if your bandwidth is not high enough and there's a very fast signal you're trying to shove through, just the signal won't actually make it, meaning that it'll get attenuated at the output. But in fact, we'll see that even beyond that, there are several issues that, due to that finite bandwidth, will cause other errors in your output. In particular, we'll see that because the resistance of the switch is actually not constant, but rather is a function of the input voltage, if you don't make the thing fast enough, you'll actually get distortion, meaning the whole thing will behave nonlinearly. And so even if you put in a perfect sinusoid, at the output you will not get pure sinusoids. We'll also see that when we try and turn these things off, unfortunately, these switches have basically charge that's hanging around in the channel. When you turn it off, that charge has to go somewhere. So that will cause, again, an error at the output. And then finally, I won't really talk about it too much further here, but of course, if your clock is not perfect, meaning it has some jitter on it, meaning it's not exactly always, perfectly well-defined phase, then that will also cause an error in terms of the voltage you're sampling, because of course, if the voltage itself is varying and the time at which you sample varies, then the voltage at the output also will vary. Okay, so let's just sort of start out by looking at a few of these issues and really where they would come from. So the first issue, or really actually several of these issues, are all basically tied to the resistance of the switch. So let's just think about sort of the simplest way that we might decide to go about building one of these things. And let me just see if I can get my pen actually back. Come on. Hello. There we go. Okay. There we go. Sorry about that. Okay, so as we've kind of drawn already, the simplest sort of switch we might think about would be something like this. So we just take an NMOS transistor and use that to drive a capacitor at the output. Okay, and let's for now just assume that the switch is actually on. Okay? So in general, you would tie the gate of that switch to VDD if you wanted to basically turn the thing on. Now, you guys tell me, if I do a plot of the resistance of the switch as a function of the input voltage, what's that plot, roughly speaking, going to look like? I don't need any, super detailed thing. Just, you can wave in the air or give me a rough idea. So if I just look at the resistance, and I'm sorry, let me call that R on, the resistance of that switch there as a function of the input voltage, what's it going to look like? I saw a few people sort of waving, or at least one person waving. So as the input voltage gets higher, what's going to happen to the resistance? Up or down? Input voltage goes higher. Remember, it's an NMOS switch. So as an example, if the input voltage is at VDD, how big is the resistance going to be? Big, small, huge? Yeah, huge, right? Because basically the transistor is off for all intents and purposes. Okay? So if we draw a plot of this, it's going to look probably something like this. Okay, and don't worry about the precise details, but let's say somewhere around here is probably the threshold of the transistor. I'm sorry. Let me actually say that that's VDD minus the threshold. Sorry, say that again. So if V is VDD, should it roughly be 1 over GM because you're treating the A power? No, so careful. Okay, so here's maybe where the confusion is. So you said if Vn is equal to VDD, shouldn't this have a resistance of sort of like 1 over GM? Now, the point here is that notice when I put this capacitor here, if I'm really waiting for a long time, then the voltage on the two sides of the switch should be completely identical. So that means that I've actually got VDD on both sides of the switch, and so my VGS is basically, in that case, would actually be 0, right? So that's actually the assumption that I'm making here, is that I'm going to put in a V in and just wait long enough for the voltage on the two sides to equilibrate. And that's exactly why, basically, once I get close to VTH, of course, the resistance just goes off to some huge number very, very quickly. Yes? Does the resistor really turn off, or will it just, the drain and the source will switch? Right? Okay, so you asked, will the drain and the source switch? Well, we have to be a little bit careful here. So it depends on which direction we were going, right? So if, for example, let's say that you started at 0 volts, and you had 0 volts on the capacitor, and then I started ramping the thing up. In that case, the capacitor side would always be the source, right? If, on the other hand, I started this at VDD, and I ramped it down, then the input side would always be the source, right? So you are correct that depending on sort of dynamically what exactly I do, which side is the source and which side is the drain, can actually flip inside of that transistor. But the plot I'm drawing here is really even saying, from a DC standpoint, if I just put in a static V in, what does the resistance actually do? All right, so this is a problem, right? Because this says that if we really want to sample signals that are up near the power supply, well, sorry, like, the resistance is going to be huge. It's going to take forever to actually sample those things. So this is a simple solution. Okay, there we go. Put a PMOS, right? So indeed, the sort of classic thing to do is take a PMOS transistor, put it in parallel, and of course, if you want it to be on, then, tie that gate to ground. Now, just to be clear, I'm going to label the resistance of that, let's call it to be RP, okay? So I'll do it in a different color. So now you guys tell me, how does that RP vary with the input voltage? Yeah, it goes the other way, right? So for high V in, it's low. And then if you get, close to the sort of VTH, or actually I should say, yeah, the VTH of the PMOS transistor, then again, it goes off to some very, very high value. So of course, because we have these two in parallel, then on the net, we're going to get something that sort of, roughly speaking, looks like this. Don't take that drawing as being precise. Obviously, really, they're actually in parallel, but roughly speaking, it's sort of taking the lower of the two of those. Okay? Now, the problem here is that notice you're still going to have some variation in that on resistance. And particularly in a modern technology where, for example, the VTH could easily be like half of the power supply, right? Notice these two things where it starts getting really, really big would kind of line up with each other. So anything that's kind of in that middle rail point would have a really, really big resistance. Okay? So this is definitely an issue that you're going to have to be careful of, because as we'll see in 1 second, the bigger this variation is, the more problems we're going to end up with in terms of the, let's say, the distortion or the accuracy at the output of the switch. But really, I wanted to mention this because, again, sort of the zero-order solution would be to do some kind of transmission gate like this. But nonetheless, don't take this as solving all problems. Because particularly, again, in these sort of modern technologies where VDD and VTH are not, there isn't a very large factor in between them, you can very easily get things that look like this where, the difference between the peak resistance and the lowest resistance could easily be something like a factor of 10 or so. Okay? And that very clearly will cause issues in terms of settling and, have to design the switches and things like this. Okay? Now, there's actually another important point that I wanted to bring up here, which is, let's say that this resistance is too large. What would you do? What's the sort of easy solution to this problem? Yeah, you just make the transistor bigger. Okay? So if I go and I make the transistor bigger, what's bad about that? What's the penalty you're going to pay? Okay, you said parasitics. So which specific parasitics are you worried about?
So if you make it wetter, your drain cap goes up.
There we go. So the drain cap is going to go up. So that certainly means you're going to be putting more load cap on the stage beforehand. That's true.
Also, so you're also going to add some load cap on the output.
There we go. You're going to add some load capacitance on the output. Now, by the way, if at the output there was a certain cap I was adding anyways, then maybe that's not so bad. But you're correct. That would also be true. Anything else? There we go. So you said you're actually going to increase the coupling, for example, from the clock, or really in this case from the gate to the source and to the drain. Okay, so more generically, let me just draw this picture one more time. Okay? So more generically, there's always going to be some capacitance from the input to the output. Now, by the way, even when the transistor is supposed to be off, so let's say that we nominally have tied this to ground here. Does my resistance actually go to infinity, or does it go to something else? Okay, you said depends on the frequency. Let's again do the DC thought experiment. So even if I put 0 on the gate of the transistor, is my resistance guaranteed to be infinite? No, right? There's always some leakage. Okay, so you not only have some so-called off capacitance, which is usually referred to as C off, you're also, of course, going to have some R off as well. So the problem, of course, is that if you size the switch up to get a low enough resistance, then the trade-off you intrinsically have to make is that your R off will become smaller, meaning that you'll have more leakage from whatever you sampled back to the input. And perhaps even more importantly, you'll have larger capacitance as well. Now, by the way, in the context of using this switch in this kind of sample and hold circuit, why is this capacitance in particular really bad? Or potentially really bad? What's it going to do? By the way, what was this circuit called in the first place? Sample and hold. Okay, so if I've got a big cap like this, what happens in the quote-unquote hold mode? Is it actually holding, or is the output still going to move? So let me give you a specific example. So let's say that the input signal we're trying to sample, let's say does something like this. And let's say that my clock, I don't know, the clock for the switch is, let's say, something like that. Okay?
Well, wouldn't the output, how much it moves, depend on the capacitance ratio between C off and C?
There we go. So you said how much the output continues to move will depend upon the ratio between C off and whatever, of course, this load is. And that's absolutely correct. But let's just sort of draw an ideal picture. Okay? So if we had an ideal picture, then what we would have wanted to see at the output of our sampler would have been something like this. But now, unfortunately, if that C off is comparable to C load, or at least is not some very small fraction of it, what's actually going to happen is something that looks, of course, like that. Okay? And by the way, if you really just upsize this switch as much as you wanted to get a low enough resistance, of course, this C off will also be very big. So, turns out there is actually one more kind of circuit trick we can play to get rid of this problem. Or at least maybe to help this problem substantially. Anybody have an idea as to how you might do that? And this is really specifically largely to fix the C off problem. The leakage problem is more problematic. Any thoughts? It's a bit of a tricky one, by the way. So.
Multiple switches.
Ah.
The
There we go. So you said you can put multiple switches and basically make it so that even though I have this C off, when I'm actually holding, I essentially see a constant voltage. Okay, so this is indeed actually exactly the idea. And by the way, this is what's known as a T switch. Okay, and you'll see why I named it that, or why it's named that in 1 second. So what we're basically going to do is we're going to take the original sampling switch, and we're actually going to split it into 2 pieces. So this will be, for example, our clock control signal. And again, these 2 switches, they're really conceptually intended to be just this one original sampling switch. But by splitting the thing into 2 pieces like this, so here I'm going to have my Vin, here I'm going to have my load capacitance. What I can now do is add another switch that I clock off of the opposite phase of the clock, connected to this intermediate point here. So the trick here is exactly what Paul was mentioning, which is now, of course, when the clock is high, I just have these 2 switches in series to drive the load capacitance. But when the clock is low, what I'm actually going to do is drive this intermediate point to ground. And the only reason to do that is because then, even if I have a C off in this half of the switch here, now at least I'm just applying a constant voltage across it. At least, ideally speaking. And so by doing that, I would dramatically reduce the coupling from this input back to that final output. Right now, hopefully I can really make it so that rather than seeing this extra blippy stuff, it's now very, very small. Now, by the way, is this free lunch? Like, did I just, improve the isolation dramatically without paying anything for it? Or what am I paying for it here? What's bad about doing this? Okay, you said I have an Elmore delay thing through these two switches. So let me say it in another way. If you want the fastest tracking bandwidth you can possibly get, do you want to put two things in series, or do you just want to have the one device? You want to have the one device, of course. Two things in series, roughly speaking, you're anywhere from 2 to 4x slower in terms of the fastest things you can possibly actually get through there. So indeed, if you're really worried a lot about the isolation, you may have to play a trick like this, but no free lunch. It will indeed slow down how fast you can actually sample. Is this clear to everybody, or? Okay. So exactly on that note, as we had mentioned already, because of the fact that my switch has a finite resistance, that's going to imply that there's a finite bandwidth through that sampling network. Now, since we've largely been talking about things in the time domain, specifically in terms of settling, I'm going to recast this a little bit as to not a pure bandwidth argument, but actually in terms of a, let's say, settling error kind of argument. And so the idea goes something like the following. Let's assume that I have a constant Vn, which is obviously a simplification, but let's just assume that it's either constant or it was an initial step that happened some time before, and that my capacitor starts initially at 0 volts. Well, so if I do that, of course, this is a very simple circuit. It's just a first-order low-pass filter. And so my output would just exponentially settle to reach whatever the input applied actually was, just like all of the other sort of first-order things we had looked at. Now, the real point here is that this basically says that if we want to get a certain bandwidth, or really equivalently a certain settling error out of these switches, then once I know sort of what the resistance is per unit width in that switch, there's going to be some minimum size for that switch that I need to use to hit this settling constraint. Right, so as an example, if let's say that I want, a 1% settling error, then I need 4.6 tau of settling. And so that's going to require me to have a certain amount or a certain value of resistance out of that switch. Now, you have to be a little bit careful because remember, a lot of times these switches are used sort of in half of a phase of the circuit, meaning, in one phase we sample and then the next phase we sort of, do something else with the charge on there. So oftentimes that 4.6 tau wouldn't have to fit inside of the whole clock cycle, but rather would have to fit in half of the clock cycle. Obviously, which means that your minimum switch size is even larger than otherwise it would have been. Now, we have to be a little bit careful about one thing here, right? The equation that I wrote here, I assumed that the output of the switch started at 0 volts. Does it really always start at 0 volts? So if I just have some arbitrary input signal here, let's say a sinusoid or something like this, does the output really always start at 0? Okay, so you said it starts at the previous thermal noise value. Certainly the thermal noise has an effect, although I think there's probably a bigger effect. So let me maybe give you a little bit of a hint. So let's say my sampling clock and the sinusoid that I'm sampling is up on the top in red there. Let's say that that's my sampling clock. So is there any particular reason that if I looked at this output over here, that every time I sort of set the clock high, that the output used to be 0 volts there? No, of course not. It's going to be whatever the previous sample actually was. Okay? So that means that you actually have something slightly more complicated now. Right? Now it's not just that you start at some 0 volt value. You can actually start at completely the wrong value. You can start at something else that, as an example, maybe one time around you sampled the peak of the sinusoid. And if you're sampling it close to Nyquist, the next time around, you could just as easily be sampling at the trough of the sinusoid. Okay? So that means you have to be a little bit careful with how you actually apply this. And in particular, in the context of sort of the stuff we talked about in high-speed links, this basically means you're going to be getting some sort of ISI, right? Some sort of inner symbol interference where the previous sample you actually had on there will sort of interfere with what you're trying to do now to actually resettle this to the correct value. So again, you have to be careful with this because that will actually put an even more stringent constraint on your settling, on your bandwidth really, or your time constant. Because it's not only that you have to sort of grab whatever the new value is that you actually have to get rid of whatever the old value that was sampled there was. Is this clear to everybody? Or?
Could it also help you if you knew that you were sampling a lot faster than your input, like you filtered your input first?
Okay. You said, so if you filtered your input first, wouldn't that actually help you? And you're absolutely correct. If you're sampling it much higher than the Nyquist rate, then obviously this problem is less of an issue, right? Because you know that the relative distance between your sample points is always going to be small. Now, having said that, that means you have to oversample, right? So you're paying for it one way or another. There is, however, one other trick that you could play, which is almost kind of embedded in the question in and of itself. So let's say, indeed, I really did not want to have to worry about this inner symbol interference. Is there anything I can do to avoid it? Yeah, exactly. You can make it start at 0. Okay, so how would you do that? Yeah, you said pre-charge. In this case, it would actually be sort of pre-discharge, right? I could just add another switch here that, for example, would be on phi 1 bar. And I'm sorry, it's not actually phi 1 bar. You have to have some sort of pulse there, right? Because obviously you need the sample at some point, right? But basically you just say, okay, well, if I'm going to have a problem with this thing, potentially carrying over previous history, let me just get rid of the history completely. Now, as I implied here, this is not completely straightforward because this implies you need sort of 3 phases of operation, right? You need sample, you need hold, and you need sort of reset. But indeed, in some cases, you can make something like that work as well. Is this clear to everybody? Or? Okay. Now, as I mentioned before, actually several times now, it turns out we're going to have some fairly interesting issues to deal with because of the fact that the switch resistance is not actually linear. So just to make sort of that effect clear, or to give us a little bit of a model for that effect, let's just again sort of take this very simple scenario. We have an NMOS sampling switch driving a load capacitor with a certain input voltage. And again, let's just look at sort of the instantaneous resistance of this thing. And in particular, I'm going to argue that sort of the model I'm going to give in 1 second is going to be valid simply because if I've really designed this circuit the right way, then it should be the case that the voltage on this side, while the switch is on, is basically the same as the voltage on this side. Because if it's not, it implies that our switch is basically not fast enough, right? We're not actually settling things out quickly enough. Okay, so if that's the case, what region of operation is the switch actually going to be in? In other words, if the two sides of the switch are really equal to each other, I should really have a VDS of roughly 0 volts. So what region of operation should the switch be in? Yeah, linear. Or triode. Okay, so that's good news because it turns out that in the triode region, the sort of ID equation is roughly the same, independent of all the short channel effects. And in fact, even if it's not, it's going to highlight sort of what the key terms really are. So if we indeed had, let's say, a so-called long channel device that was in the triode region, we could say that the drain current is just mu Cox, W over L. And now I'll ask you guys, what are the sort of voltage terms that I would put into there in general? Okay, so just to be absolutely clear, there'd be a minus VDS over 2 times VDS. Okay? Now, in our specific case, what is VGS minus VTH minus VDS over 2? In fact, just what's VGS minus VTH? Yeah, there we go. It's VDD minus VTH minus Vin. And then we have our minus VDS over 2 times VDS. So of course, if we're interested in the resistance, we can just take the derivative of that with respect to VDS. And now here's where we'll assume that VDS is actually equal to 0. Right? Then this will just become mu Cox W over L VDD minus VTH minus Vin. So why did I go through and bother saying that? Well, what this basically tells us, and I'm going to write this in a slightly different way, is that the on resistance is just L over W times 1 over mu Cox VDD minus VTH times 1 over 1 minus Vin over VDD minus VTH. Okay, now this looks a little bit funny. All I really did was just sort of pulled out the VDD minus VTH into the front here. Because what I really wanted to highlight was that this whole thing here is really just some constant. Right? It's just some fixed resistance that depends upon your threshold, upon your VDD, upon the transistor characteristics, width and length, and etc. Right? So that's basically just some number. Unfortunately, however, we also have this term, which is now signal dependent. Okay, because obviously as Vin varies, that goes and multiplies the whole on resistance based upon this variation. And as we talked about before with a purely NMOS sampler, the larger Vin is relative to VDD, the larger this resistance is actually going to be. All right, so turns out this effect can actually cause some pretty, let's say, interesting problems in our circuits. And in particular, as I mentioned before, what this basically says is that now if we think about sort of the model for our circuit, instead of it just being, a resistor and a capacitor, now this resistor actually depends, that resistor is actually some function of Vn. So as soon as you've got, let's say, a signal-dependent resistance, well, sorry, this is no longer a LTI circuit. This is no longer a linear time invariant circuit. It's actually a nonlinear, perhaps time invariant, but a nonlinear circuit. Okay? And as soon as you have nonlinear circuits, now you have to actually worry about what's going to happen as you apply different types of inputs into it. Meaning, in particular, you can't just sort of say, well, everything is a sinusoid and I pass through some transfer function. Now the whole thing actually has some, let's say, perhaps non-intuitive behavior. So in order to characterize the sort of importance of this effect, your first instinct might just be to say, well, okay, fine. Let me just go and plug this thing into SPICE and see sort of how bad the effect really is. The problem, however, is that these things are really, really sensitive to the transistor model A, and B, especially if you're shooting for a very, very high resolution kind of thing, let's say 10, 12, 13, etc. bits, you have to be really careful with how high you turn the accuracy settings in SPICE, because if you don't really get them just right, very easy to get big mistakes in this. So what I want to show you next is sort of a simple, even MATLAB-based kind of thing you can do to at least give yourself some way of validating what SPICE tells you about the errors that are being caused here. So the particular test that tends to be the most relevant in this kind of scenario is you basically take your switch, apply, of course, VDD at the gate, have your load cap on the other side, and then essentially just apply a sinusoid at the input. And again, you'll have to forgive my artistic skills here. Let me try and do that a little bit better. But you basically apply a sinusoid at the input. Okay? So if our sort of switch there was, perfectly linear, meaning its on resistance was totally constant, then of course this would just be an RC circuit. And so if you looked at the output, you should just see a perfect sinusoid, maybe scaled in voltage and with a different phase, but still just a perfect sinusoid. So the model that I'm going to use to then try and figure out how bad this thing is from a distortion or nonlinearity standpoint is just to say, well, look, this whole thing is still an RC circuit, which means that I still should be using this simple sort of time domain equation to figure out what the output would actually be. Right? This is just assuming the input was a step and essentially looking at the settling time over here. But notice that now, instead of just having a fixed tau, right, which would have just been that R naught times C, instead I'm going to multiply it by that sort of input voltage dependent effect, right? We said that our resistance actually gets increased by this 1 over 1 minus Vin minus VDD over VDD minus VTH. I'm just going to take that factor and have the tau effectively be modified by that factor there. Okay? So if you do that experiment, you actually see something pretty interesting. So what I'm showing you here is basically an FFT of essentially the output of that switch for some given sinusoidal input. And what I've done here is that I'm changing the period of that sinusoid relative to the nominal time constant of my switch there. So as an example, you can see that if I make the period of the sinusoid 10 times larger than the time constant, then what you'll see is indeed you get this sort of main tone at, in this case I just put it at whatever, 0.07 of the sampling frequency. But now you actually get these other harmonics. Right? In other words, you don't just get the pure sinusoid, you actually get these extra harmonics. And in general, for all of these nonlinearities, what you typically care about is essentially the signal to distortion ratio, meaning how big is the actual sort of linear real signal you wanted relative to these extra harmonics that pop up. And so what you can see here is this, sort of third harmonic here is about 50 dB down from that main signal. So you guys tell me, if I was building, let's say, a, 6-bit system, let's say a 6-bit analog to digital converter, is this sort of okay, or is this a problem? Yeah, exactly. Generally speaking, it'd be fine, because my quantization noise would be way above this, right? My quantization noise would be at something like, minus 38 dB or so, right? Well, okay, so now let's say I'm trying to build a 10-bit system. Is this a problem or not? Yeah, it's a big problem, right? For 10 bits, I wanted something like, 60 plus dB of dynamic range. Well, notice this third order tone here is sitting right at minus 50. And so it would basically cause me to lose something like a couple of bits of effective resolution. So what this is really getting at is that, notice if I was to sort of decrease that nominal time constant, or rather equivalently make the period of the sinusoid longer compared to that time constant, so here's where I've done t over tau of 20. Now notice by doing that, I went from about minus 50 dB to about minus 70 dB for that third order tone. So now I could actually do the sort of 10-bit type of system. So the real point here is that if you do indeed have this kind of distortion, what it'll tend to force you to do is actually over-design the switches. In other words, you won't be able to just use sort of what you nominally would have expected based on the linear calculation. You'll actually tend to have to make the switch even faster than that, just to make sure that the sampling distortion doesn't end up killing you. Now, by the way, maybe just to make sure it's clear, intuitively, why is it that if I make the sinusoid slower relative to the nominal time constant, why does that make this distortion get smaller? Like, why do you see that pretty substantial improvement there? Intuitively, what's happening? I'll maybe encourage you to think about this model here. Yeah? Yeah, exactly. So in the limit, if you make the input really, really slow, I actually don't care what the hell you did with this resistance, right? Even if that resistance became really, really big, as long as I waited long enough compared to whatever that time constant was, then the two sides of this will indeed go to the same voltage. In other words, there's no sort of, unless I do something really, really funky, there isn't any, let's say, reasonable nonlinear resistance I can place here that would make it so that at DC, the two sides of that resistor don't go to the same voltage. So in other words, by making the input slow compared to even the nominal time constant, I can dramatically reduce the distortion simply because I just make sure that I get the voltage on the two sides of the switch to be as close to each other as they can as possible. Does this make sense to everybody? Or? Okay. So, we said that sort of what I end up having to do is kind of over-design the switch, right? And one way of doing it was actually to make just all of the inputs slow compared to the sort of nominal time constant you get. But as you can imagine, at some point that becomes painful, right? Because if I want to run this thing very, very fast, then it may be actually very hard to make that constraint hold true. Is there anything else you can do? Is there any other sort of game or trick you can apply to try and get around this distortion issue? Or am I just sort of stuck? And by the way, I don't even need to modify the circuit just yet. Okay, you said you can boost VDD somehow. So indeed, if I can just make VDD instead of a volt, 2 volts or something like that, great. That will certainly help. Unfortunately, I can't always quite do that, at least not without destroying the switch. But is there something equivalent? There we go, lower Vin, right? So if I reduce the Vin, then that means that this whole thing here, which is just the whole cause of the distortion in the first place, relatively speaking, will get smaller, right? So if rather than, let's say, using a 0 to 1 volt Vin, I only use, I don't know, 0 to 100 millivolts or 0 to 200 millivolts or something like this, indeed, you can substantially reduce the distortion as well. Now, by the way, why is it that, what's the penalty you'd pay if you indeed just reduce the swing? Or the potential penalty, I should say. Yeah, SNR, right? So basically that means that if I have a smaller input swing, then for the same thermal noise, my SNR will be worse. So if you're in a heavily SNR limited regime, then reducing that input swing would also be quite painful, because it would force you to spend extra power in terms of larger capacitors and etc. to actually get back the SNR you were interested in. Having said that, if you really want to go to these very, very high speeds, where you're just sort of fundamentally limited by that sampling distortion, you may not have a choice. You may have to go to these lower signal swings just to actually get the sampling speed you want, and therefore spend a lot of extra power just to make sure that you have the SNR that you're interested in as well. Does this make sense to everybody? Or? Okay. So there is actually one other trick, which is kind of like the, let's say the jackass solution, but turns out it's actually quite a good one, which is, again, it's one of these things where you say, doctor, it hurts when I do this, and the doctor says, well, don't do it. Okay? So again, the whole problem was coming about here, because basically, as the input signal was varying, the VGS of your sampling switch was also varying. So the idea here is, well, what if we can get rid of that variation in the VGS? What if we can just make it so that no matter what the input voltage is, I always apply, let's say, a VDD of VGS across my sampling switch? So you might think that this is kind of impossible, but actually, conceptually, it's pretty straightforward to do. So the idea is the following. When the switch is off, fine, just tie ground onto the gate of the NMOS transistor, it's off. When you want it to be on, rather than applying basically VDD from the gate to ground, instead, let's take this so-called floating battery and apply it from the source to the gate, so that the VGS across the switch is always VDD, regardless of what the input is actually doing. So indeed, if you do this, now actually in terms of this distortion, life is much nicer. Because now what I've basically done is I've completely gotten rid of this term here, at least ideally speaking. And so indeed, I'll still have sort of a settling error due to the finite R on, but that will still be a purely linear settling error. Right? Now I can just design the width of the switch to actually hit the settling spec I want, and not have to worry about playing around with the input swing or anything, or anything like that to hit the distortion specs I'm interested in. So you guys tell me, how can you do this? How do you build this sort of quote-unquote floating battery kind of thing? How am I going to get it so that the gate voltage across the sampling switch is constant? But in other words, this relative to ground tracks with the source. Yeah, exactly. The best way to approximate a floating battery is usually a capacitor. So let's actually draw how we might do that. So let's take my original sampling switch. It just looks like this. And so what we're basically saying is something like the following now. Okay, so as we said before, in the first phase, let's just call this, I don't know, phi 1. We just want the gate of that switch to be at ground, right? Well, it turns out what we're going to do is during that same phase, we're actually just going to pre-charge a capacitor to VDD. Okay, so these will also both be on during phi 1. So now, during phi 2, when I actually want to do the sampling, and by the way, just to be clear, this is where Vin is going to be coming from. Now when I actually want to do the sampling, all I have to do is connect that capacitor from the input to the gate of the sampling transistor. Right? And as long as that capacitor is big enough, then indeed this voltage here should just track, should basically be always VDD above the input voltage. So just to draw that to make sure it's clear, let's say that this is our Vin here. Then what the sort of gate voltage would look like is, of course, initially it would be at ground. Then when you actually want to do the sampling, it would jump up, track the input, get turned back off. Let's say again, jump up, track the input, get turned back off, and so on and so forth, right? Jump up, track the input, turn back off, and so on. Okay, so in other words, and again, you'll have to sort of forgive my artistry, but what should really be happening is that whenever it's on, there should be a constant VDD of voltage above the input on the gate of that switch. And by the way, just to be clear, this is VG here, that's VG. Make sense to everybody? Now, you guys tell me, are there any problems with actually building this? Is this just going to work perfectly the way I described, or is there some stuff we're going to have to be careful about? So by the way, can you apply any voltage you want to a transistor? You know, if we took our 90 nanometer transistor and put, I don't know, 10 volts from its gate to its source, is anything bad going to happen? How many of you guys have actually tried something like that? Ah, you did try. Okay, good. And what happened to the transistor? Didn't make it. Right. Smoke usually comes out, right? Something blows up. Okay, so now why I'm asking in this particular context, what might be a problem specifically related to that in this circuit here? The DC level on your Vin might be screwed up. Why would the DC level on Vin be messed up?
I don't know, somehow, whatever circuit happens before this might.
Oh, okay. You said there might be some weird coupling there. That's certainly possible. Let's maybe even actually focus on just this part of the circuit. So let's not even worry about the thing driving it. When I put switches here, what do I actually have to build those out of? Transistors. Okay. So let's just sort of try something out. So what might you build this switch here out of? So you said NMOS, but usually when you're passing VDD, it's usually a PMOS, right? Well, by the way, it's going to turn out that your original answer was correct, but now we're going to see why. Okay? So let's actually try and put a PMOS here. All right, so by the way, there's always that hidden terminal on the PMOS, right? There's that body terminal. Where do we usually tie that body terminal? Yeah, we usually tie it to VDD, right? We usually do that. All right, now here's where we have a problem. So that gate right there, or that node right there, what's the highest voltage it can actually go to? And let's assume that Vin is anywhere from 0 to VDD. Yeah, that can actually go all the way up to 2 VDD. And remember, during that time, that switch that I just sort of highlighted with the arrow is actually on. So what's going to happen to this PMOS transistor? And let's just assume we turned it off at that time. So let's pretend that this was at VDD here. What's going to happen to this PMOS transistor if there's actually 2 VDD here, and we've got a PMOS right there? What state is that switch actually in? Yeah, it's on, right? We wanted it to be off. Now, by the way, it's actually even worse than that, because if I were to draw in the diode associated with the drain of this PMOS and its body, which way is it pointing? Yeah, that diode is actually also on. Okay? So in other words, there's actually a diode pointing like this. Okay, so that's bad news, right? Not only is the transistor on when it wasn't supposed to be, actually we just forward biased the diode, which typically, if you're not careful, also tends to, let smoke out in various ways. Okay, so clearly we can't just put sort of a PMOS transistor here. And really maybe the meta or more important point is, I've got things that will go actually outside of the power supply rail. And trust me, modern transistors, if you go to just double the supply voltage and you just directly apply it to the gate and it's there for any long period of time, maybe it doesn't blow up right away, but you certainly will not have the lifetime you wanted. So the point here is that we really have to be very careful with how we build all of these switches to make sure that because we have things going outside of the power supply rail, that A, we don't blow anything up, meaning we don't cause things to actually physically fail, and B, that the switches actually behave the way we expected them to in all of the different phases of operation. So what I'm showing you here is actually one of the sort of, let's say, classic implementations of this idea, which, by the way, was actually sort of proposed and first demonstrated here at Berkeley about, let's say, 10, 15 years ago or so. So this was done by a guy named Andy Abo. And so what I'm showing you here is how you'd really actually build all of the different switches that I showed you to actually implement this constant VGS sampling circuit. So by the way, just to be totally clear, this thing in the red box here, that's the actual sampling switch I'm interested in. Everything else in this picture is just to generate that constant VGS sampling. Okay, so at first glance, you should see that this is not necessarily the most straightforward thing to do. Right? There's a lot of extra complexity you have to introduce just to get this to happen. Okay? So let me just kind of briefly walk through what's going on here. So this piece that I've highlighted on the left over here, this is what's known as a clock multiplier, or sometimes also referred to as a charge pump. And the idea is actually pretty simple. It's just a very simple way of making it so that you can actually get signals that instead of swinging, for example, between 0 and VDD, will actually swing between VDD and 2 VDD. So let's just see sort of how this thing might actually work. So let's just pretend that we're kind of at the beginning of time and we haven't really done anything yet. So if I just have, and by the way, these are NMOS transistors here. So if I just have these NMOS transistors sitting here and that they have some leakage in them, what would the voltage on these nodes initially start at? Again, I haven't done anything at the beginning of time. I'm just, letting things leak. Where do those two voltages start? Yeah, they have to start at VDD, right? There's no other current path, and so they have to be at VDD. All right, well, what's going to happen then when, for example, this clock transitions low, which of course means that this node here will transition high. And in particular, what's going to happen on this node right here when that clock transitions high? Is it? This node right here on the right. So notice this side went from ground up to VDD. Yeah, it's going to have to go to 2 VDD, right? Because it initially was at VDD and the other side was at ground. So if you boot the bottom side of the capacitor, the other side just tracks it, right? Because you can't instantly change the voltage across the cap. So this will now jump up to 2 VDD. And now, interestingly enough, if that node jumps to 2 VDD, guess what? This NMOS transistor turns on. And notice, it will hold this side here at VDD. Okay, so similarly, when the clock actually goes the other way, so when that edge happens there, and this edge happens here, then this will also go to 2 VDD, just like the other side this did. And of course, this one will come back to VDD. So why did I bother doing all of this? Well, notice by doing this, I can now create a signal that, again, as I said before, swings from VDD up to 2 VDD. What's useful about that is that notice, you remember we said before that I was going to end up putting an NMOS transistor for the equivalent of this switch, which is the one that precharges the capacitor to VDD? Well, that's exactly what I've done here. And so the reason I wanted this VDD to 2 VDD signal is because if I want that NMOS switch to actually charge the cap up to VDD, I need a voltage that's above VDD to apply to the gate of the transistor, right? And this charge pump or this clock multiplier circuit that I showed on the left is exactly the way I built that voltage. So just in one phase, it's going to have 2 VDD roughly on this gate here, which turns on that M3 and gives me VDD on that node. And then the other phase, when I want to turn it off, I just bring this back to VDD. And even though it looks really funny, right, you have an NMOS with VDD on all 3 terminals. If you think about it, all voltages are relative. No difference between VDD on all 3 terminals and ground on all 3 terminals. Either way, transistor's off. Okay? Other thing I should mention is, of course, by putting the NMOS here, remember we said that we had that diode problem? Well, if I just tie this thing to ground, and all of the other terminals are at VDD, or even 2 VDD or whatever it is, well, nicely enough, diode never turns on. Right? I've always got a reverse bias on the diode. Make sense to people, or? Now, there's actually a couple of other tricks that had to be played here. So the first is that this transistor here, which unfortunately is maybe a little bit different or a little bit hard to see, but it's actually a PMOS transistor. So that guy there, when I want to turn it on, you have to be kind of careful with what voltage you apply to its gate. So in particular, just as a reminder, this node here can swing anywhere from ground all the way up to 2 VDD, right? So if we want to turn this PMOS transistor on here, let me draw this in a slightly different color. Let's just say that when it was on, I just tied its gate to ground. What would be the problem with that? What would you be doing that we just said is bad? Yeah, exactly. The VGS would be 2 VDD. And maybe that's, okay for, a couple of cycles or something, but over the long term, in general, that's bad news. It causes the transistor to break down. Okay? So that means that when the thing is on, you actually cannot just tie it to that. Instead, you actually have to tie it to somewhere that's, basically in between the middle of the rail. Okay? So in other words, when this PMOS is really on, what you'll generally do is tie it to, for example, VDD. Okay? Because you know that this node here will always be above that point. Okay, similarly, if you notice this switch over here, which again, just to be clear, is the switch that's just tying the gate to ground. Notice it's not just a simple NMOS transistor. I actually added this extra device M7 in here, whose gate is always tied to VDD. Well, even though this is kind of a digital circuit, in reality this thing is acting a lot like an analog thing. So in other words, this thing here is basically just acting like a cascode. Okay, and the idea is very simple. So as we said before, that intermediate node here, or rather the gate of the sampling switch, can go anywhere from ground when it's off, all the way up to 2 VDD when it's actually on. Well, just like before, if this was at ground and we just directly put 2 VDD on it, again, we might break the transistor down. So what this extra switch here is doing is it's just trying to limit the voltage across that lower switch. And in particular, because I put the gate, because I put this gate at VDD, it's an NMOS transistor, right? So that means that this voltage here, basically at its highest, should never really go above VDD either. Right? Because if it went above VDD, that means we actually have a negative VGS on that cascode switch. Well, again, that's good news, because that means that now I only have at most VDD across this switch, even though across sort of the entire composite there, I've actually placed 2 VDD of voltage. Is this clear to everybody, or? Okay, so really the most important take-home message here is that you can indeed actually build these constant VGS types of sampling circuits. In other words, you can play some tricks to get rid of a lot of those switch distortion effects. Having said that, however, especially if you're trying to go at very, very high speeds, it can be pretty difficult simply because you end up having to build a lot of extra circuitry that basically creates voltage signals that are swinging at much larger than they otherwise would have been. So in particular, this gate of the sampling switch has to swing anywhere from ground all the way up to 2 VDD. And so if you want something that's very, very fast, all of the sort of extra, cascoding and other, more complex structures you did tends to be a very, very big overhead in doing it. The other thing I should mention is that even though this does help quite a bit with the distortion, it's not to say that it completely eliminates it. Because there is still one more source of basically, it's not really VGS per se, but it's actually VGS minus VTH variation that we still have not gotten rid of yet. So can anyone sort of tease out what that is? And I'll give you a hint. It's related to a terminal that, again, we don't typically tend to draw.
Body effect?
Yeah, exactly. It's the body effect. So if we look at the actual sampling switch, if I tie this body to ground, well, unfortunately, that means the source to body voltage, again, varies with the input. So clearly that effect is much smaller than having the VGS vary, but it's still a non-zero effect. Okay, so even after you've gone to all this trouble, it's not to say you're going to be perfect. It's going to be that you're still going to have some remaining errors due to that. By the way, it turns out that it's actually not even just due to that. It's also that this capacitor here is obviously not going to be infinitely large, right? And so if there's any sort of stray parasitics on this node, the gate of the transistor won't perfectly track with the input voltage. In other words, there'll always be some remaining variation in the actual VGS. Make sense to everybody here? All right. Lest you thought that we were done, that these are the only errors in the world we have to worry about with these switches, unfortunately, we're absolutely not. Okay? So as I mentioned before, if we again sort of take our very simple sampling switch setup, where we have this VIN, and we just have some NMOS transistor, of course its gate is tied to a clock, and we just connect that output to a capacitor. Well, if you actually watch what happens when you turn that switch off, so let's say we look at VIN, and I'll just draw it in a different color. Let's call that VOUT. So let's say that VIN was actually constant. It looked something like this. If we actually draw VOUT, what you'll see is it'll do something like this. And the reason is fairly simple. So remember, whenever you turn a transistor on, there's always some charge inside of the channel. In this particular case, it's an NMOS, so there's always electrons sitting inside of the channel. Well, when you turn that clock off, those electrons have to go somewhere, right? They can't just magically disappear into thin air. And unfortunately, what tends to happen is that some fraction of them will actually flow into your output. So what that means is that if you look at this output over here, there's always some finite error between where you actually wanted to sample, meaning where the actual output was supposed to be, and where it ends up being due to this charge injection effect. So by the way, don't ask me why, but this is usually called a pedestal error. Has something to do with, I don't know, the output just being sort of lower than the input was supposed to be. Again, not sure how they came up with this terminology, but if you hear it, that's what they're referring to. And what it really says is that your output is first of all going to be shifted, right? There's going to be some offset from where the real output was supposed to be. But second, and perhaps more importantly, it's actually also going to cause some distortion. Because if you think about it, the charge that's inside of the channel there, again, depends upon the VGS that you're using. And so unless you use this sort of constant VGS kind of sampling switch trick, then unfortunately, the charge you get will depend upon the input, and therefore the error you get will also depend upon the input, perhaps in some nonlinear or non-obvious way. Is this clear to everybody, or? Okay. So let's just sort of take a look at how bad this might actually be. And in particular, maybe the most important thing to realize here is that unfortunately there isn't really much you can do about this, at least from zero order from a design standpoint. Because the problem is the following. Remember, we said we needed a certain width in that switch in order to get our settling constraint, in order to get our bandwidth. Well, if I have a certain size switch, that also means there's a certain capacitance associated with that switch, which therefore means there's a certain charge inside of the channel. Once I have a certain charge, that charge, of course, just gets dumped into the output capacitance. And basically that means that there's really nothing I can do. In other words, because I had to size this switch to be proportionally, or rather, the size of the switch is really proportional to the load capacitance you're driving in the first place, which again is coming from the bandwidth constraint, then the amount of switch error you get is a fixed number, or charge injection error is really a fixed number. Right? Because again, let's say I double the size of the capacitor. If I want the same bandwidth, I also have to double the size of the switch, which means the charge will get doubled, and the relative voltage error will be fixed. Okay? So again, especially if you're running at very, very high speeds, relative, of course, to the sort of intrinsic bandwidth of the technology, this can become a very, very big voltage error. Because your only choice or your only mechanism to actually hit that speed is to make the switch large, which means that relatively speaking, the charge you dump out ends up being big compared to the sort of capacity or the total charge on the capacitor. So just to give you an idea, this is sort of a specific technology, not really relevant to your particular technology, but this is a relatively old one. Just as an example, you can very easily end up with things that are tens of millivolts to maybe even 100 plus millivolts in terms of this charge injection error. And so if you're talking about dealing with things at 8, 10, 11, 12 bits, this is like many, many LSBs, right? Very, very big error. So definitely not something that you would want to just sort of ignore or leave as is. So there are a few, let's say, tricks that people have come up with to try and at least mitigate this effect. Turns out that exactly canceling it, again, is really, really difficult. But there are some tricks you can play to at least make things a little bit better. And the first one that I want to mention, just because it's kind of a cute trick, is that the thought process kind of goes something like this. My original problem was that if I looked at that sampling switch, when I turned it off, there was some charge that had to flow out of that switch, and because it had nowhere else to go, it gets dumped into a capacitor, or dumped into my sampling capacitor. So the thought process of this particular idea is to say, well, what if instead of letting that charge go on to my capacitor, I actually give it another path that I know will suck up exactly that amount of charge? Well, how do you do that? You basically build another transistor that you clock off of the opposite phase of the clock that turns on exactly when this switch turns off, right? So that as long as the charge this switch needs in order to turn on is the same as the charge that this switch would have been dumping out, then ideally speaking, there should be no residual error, right? You're just moving charge from one channel over to the next. Now, this is obviously not quite as straightforward as I may have described. And sort of the reasons are maybe, let's say, indicated somewhat on the slide here, but let's see if we can sort of tease it out of you guys. So first of all, as I've mentioned here, I said that I sized the main switch to be W, and the secondary or so-called dummy switch to be W over 2, in other words, half of the width. The reason I did that is that what I assumed was that if I had a certain amount of charge Q in that sampling switch, I'm assuming that half of it is going to flow to the right, and half of it is going to flow to the left. So that when I then turn on this dummy switch, which by the way, notice, it's really just a transistor with its drain and source connected together. So in terms of, let's say, functionally, in terms of, the behavior of the circuit, really it's not supposed to be doing anything, right? All it's doing is just turning this transistor on and off. So the idea, of course, is that if really half of the charge flows to the right, then if I size this transistor to be half the size of that one, it should exactly grab up that amount of charge. Unfortunately, however, life is not quite that simple. So, the question, of course, is, will it really be that half goes to the right and half goes to the left? So you guys tell me, is it not always going to be the case or not? Is it always that the charge should just magically decide to split, halfway left and right? Ah, there you go. So you said it depends on these two capacitors, right? The CD and the CS. So in particular, what would have to be true about those capacitors in order for it to split perfectly evenly? Yeah, so ideally they'd have to be perfectly equal. But unfortunately, life is actually even more complicated than that. So, what's this R doing here? How would that R potentially affect things? By the way, when you said it would split equally between the two sides, if these two capacitors were the same, why is that? Like, what was the sort of underlying mechanism that would cause it to split equally between the two slides? Okay.
So all the charges will decide to evenly.
So you said if they're equal, then they can both hold equal charge. That's true. But let's think about this from a, let's say, very basic, first order kind of circuit standpoint. Yeah.
I is proportional to C times omega, so current will split in time on either side.
Okay. So you're actually getting much more in the right direction. So let me ask it maybe in a slightly different way. Let's say I told you that there's some charge Q just sitting there out in space somewhere. And then I told you that there's some resistance to go to the left and some resistance to go to the right. How is that charge going to decide which way to move, or really more accurately, how to split in terms of how it moves? Yeah, so you said it's going to prefer the low resistance path. That's correct, but more, let's say, precisely, it's going to obey current divider, right? Because either it has to obey, let's say, basically if there's, implicitly I'm saying there's a short circuit here and there's a short circuit there, it has to obey KVL, right? Because the voltage from here to there would have to be the same as the voltage from here to there. So that would mean that, of course, some fraction of the charge will flow to the left. And obviously, the smaller R left is, the larger that fraction will be. And some fraction will flow to the right. Okay? So in other words, what we're really getting at is that if these two capacitors were the same, that's implying that the impedance looking on the two sides is the same. Now, the rub in the ointment, or the issue here, is that, unfortunately, even if these caps are exactly the same, right, there's lots of other impedances in the circuit. Right? So there might be some source resistance. There might be some additional capacitance from the next stage. In fact, that might even have some input resistance. So it turns out that in general, it's actually pretty tough to get this exactly right to split equally between the two sides. And in fact, the game that this particular paper played was they actually intentionally added this resistance in here because what they wanted to do was they really made CD and CS be the same, but they then added this resistor in so that at least for the fairly fast kind of dynamics of the charge getting sort of pulled out of that transistor there, you were mostly dominated by the impedance of this capacitor and this capacitor. So in other words, they added this resistor in to try and force the charge to split equally between the two sides, so that then when they used this dummy switch, the cancellation really actually worked the way they wanted it to. So if you sort of pay close attention to this table, what this column here is saying is if you didn't have any dummy switch at all, how big the charge injection error was, and you can see it's quite large, right? All the way up to like 160 millivolts. If you then added this dummy switch in, but didn't add this resistor, or didn't sort of play all the tricks to balance the switches out, then you substantially reduced the error by about a factor of 4 or so, but still it was relatively substantial. And then finally, if you played these extra tricks, so you really balanced these capacitors out, you added that series resistor in, then you could really sort of fairly substantially reduce it, down to the kind of single millivolt type of range. Having said that in particular, what's annoying about adding that in? Or what's bad about doing that? Yeah, it hurts your bandwidth, right? You just put a resistor in series with your high-speed signal path. So clearly, it's going to make things worse from a settling time standpoint. So, to make life even, let's say, slightly more complicated, you saw that these guys went through a lot of trouble to try and sort of force the charge redistribution to be equal. Well, turns out that's not so straightforward of a thing to do. And in fact, even knowing for sure that it's going to do that is pretty complicated. Because if you really sort of think about it, what's actually happening here is that we are really sort of interested in the very, very high frequency dynamics of what happens when you turn a transistor off, and sort of what happens to the both charge and effective channel resistance. So a kind of simple model of thinking of that is, let's say we take our switch, and we just have capacitors on the two sides. Okay? Well, one way you can kind of model the behavior of that switch is to kind of break it up into a bunch of smaller chunks, right? Where each of those chunks, I'm just going to model with a resistance, where that resistance is proportional to 1 over the charge at that local spot in the switch. Okay, so by the way, just to be clear, implicitly there's kind of the gate of the switch is up above here somewhere. So if you really want to know what's going to happen to the charge, you have to do this kind of analysis where you basically would say, okay, look, initially I would have something set up like this where I would essentially have these distributed resistors where each of those resistors is inversely proportional to the instantaneous charge. And what you would do is you'd basically say, well, okay, at the initial time, if this was my state, here's how much charge would either flow to the left or to the right for each of these sort of sub-segments. And then what you'd basically do is you'd repeat this experiment with, very, very small time steps until eventually you saw that all of the charge either ended up on the left-hand side, or excuse me, not all of the charge, some fraction of the charge ends up on the left-hand side, and some other fraction ends up on the right-hand side. And by the way, this actually also depends, obviously, on the sort of initial conditions of this thing, right? So if this voltage and this voltage are not exactly the same initially, again, that's going to skew which way the charge actually will flow. Now, there's kind of a good and a bad news here. The good news is that, if you really want to do this kind of analysis, it's been done before. I've given you sort of a reference here. So you can actually go and take a look at sort of, procedurally what you would do. And one of the interesting results there is that actually which way the thing splits depends upon how fast this gate signal is relative to the sort of intrinsic time constant of the switch. But the bad news is that SPICE doesn't actually naturally do this for you. Okay? So in other words, if you go and you take a circuit that looks like this and you simulate it in SPICE, almost guaranteed you're not going to get the right answer. Because the problem is that to really get this right, SPICE would actually have to do exactly this kind of modeling procedure, which if you think about it is really, really complicated, right? In general, you don't want to have to sort of model the distributed, very, very small scale effects of the transistor. At least not if you want to make your simulations run at any reasonable rate. So in SPICE, instead, what they typically do is they come up with this so-called XPart parameter. And this is typically just something that's set somewhere in the model file. And based upon this parameter, SPICE just doesn't even bother trying to figure out what the charge injection does. It just says, look, if you set XPart, for example, to be equal to 0, I'll take 60% of the charge and send it to the source, and 40% of the charge and send it to the drain. If you set XPart equals 0.5, I'll make the split be equal. If you set XPart equals 1, I'll send all of the charge onto the drain. So in other words, just based on this one parameter, it will sort of, you'll say, arbitrarily decide how much charge goes into what. So the problem here, of course, is that unless you really know what the whole circuit setup is, there's no way for you to really know what the right thing to do here actually is. So that's why you really need to know about this distributed kind of analysis, because if there's some circuit you have that really is very highly sensitive to this charge injection, your only choice really is to do this type of analysis to at least give you some estimate as to how bad the problem may be. Now, having said that, the other, let's say, very practical thing that people will do is they'll try and come up with a worst case, right? So they'll say, well, you know what? I don't know how big the charge injection will really be, but if I dump it all onto one side and I make sure that that side is the bad side, then, maybe that'll give me an idea of sort of what the worst errors possibly could be. Now again, even there you have to be really careful, because obviously, especially if you have a trick like this, where you have another switch that's intentionally trying to compensate the effect, figuring out what the real worst case is kind of tricky. Because again, it all depends on how you size this relative to how the actual charge splits between those two scenarios. Does this make sense to everybody, or? Yes?
When it says 100% drain, how does it determine which terminal is the drain? Which one do you draw as the drain?
Okay, great question. So the question, just to repeat, was, when you say 100% drain, how does SPICE decide what the drain actually is? Well, here's how SPICE decides. Right, when you instantiate a transistor, right, the order is drain, gate, source, body. It's literally based upon which terminal you tied to that first thing there. So this is actually a very annoying property in the sense that SPICE, unfortunately, especially if you set the parameter like this, intrinsically will have an asymmetry in the device. When in reality, the actual transistor doesn't care anything about what side is the drain or what side is the source, right? So in other words, you have to be really careful about this, because this is a great way to have all kinds of weird simulation effects happen, simply because of the way SPICE has to model these charge injection effects. So that's actually a great question, and this is something that you should keep in mind, because I think we'll finish this up on Thursday, but you'll see this actually has implications on how you'd have to build some of the, even in simulation, some of the sort of types of switches we'll be dealing with. Because if you don't build them the right way, these asymmetries will basically cause all kinds of bogus things to happen. Great question. Other questions on this, or?